The outage is not the real cost. Technical debt is far more likely to slow releases, raise change risk, and make every update harder to ship. As for the biggest headline dollar figures often cited in industry reports, they are difficult to verify and should be treated cautiously. This is no tech. If technical debt usually does not announce itself with an outage, what is it really costing the enterprise every day? We have been conditioned to think of legacy code as a ticking time bomb. When we hear the term technical debt, we picture dramatic public failures. Because of these events, we assume bad code equals a broken system. And the industry has tried to put a massive price tag on this problem. In 2022, CISQ reportedly estimated that poor software quality cost the U.S. economy $2.41 trillion, including about $1.52 trillion attributed to technical debt. But we need to stop right here. While these multi-trillion-dollar figures are widely cited in industry reports, they are difficult to verify independently and should be viewed as broad estimates rather than audited facts. Which means we cannot just accept a trillion-dollar label and move on. Can one code metric really tell you what technical debt costs the business? Hold that question, because the answer only makes sense after we compare proxies, delivery metrics, and actual operating pain. Open a code review diff for a legacy application. At first glance, the system works perfectly fine. Traffic is flowing, customers are checking out, and the servers are up. A software system can stay online and still get costlier to change. This is where the real tax is collected, not in the dramatic crashes, but in the slow merge. When a slow merge becomes the default, product managers stop asking for small improvements. The business learns to batch changes into massive, risky releases because the overhead of shipping anything is just too high. Look at what happens when a developer tries to add one new field to a database. In a clean architecture, this is a local change, but in a highly coupled legacy system, that single field addition breaks 5 downstream services. The billing service throws a validation error because it expects a specific payload size. The notification service crashes because it relies on an outdated object relational mapper that cannot handle the new schema. A seemingly small choice can create recurring debt when every schema change, API version bump, or library upgrade requires cross-team coordination. An engineer does not just write the code. Engineering time is consumed by architecture review, implementation, test harnesses, CI/CD changes, security review, observability, rollback tooling, and repeated upgrades. A concrete example is dependency risk, where a single library choice can force emergency patching across dozens of services. Real-world events like Log4Shell turned a vulnerable dependency into a widespread operational firefight, while Heartbleed similarly created massive, unplanned patching and certificate rotation work. And when the codebase is brittle, you start seeing the red build. A red build is a small sign of friction. It means a test failed because of a race condition nobody understands, or a linter caught an edge case that was never documented. By itself, one failure is just a minor annoyance. But multiplied across 50 engineers over 6 months, that friction accumulates into massive organizational drag. It looks like an outage problem, but it is really a delivery problem. The everyday tax of uncertainty, rework, and delayed shipping quietly drains the engineering budget. Move from that code review diff to the static analysis panel.
When management realizes that legacy code is slowing them down, they usually look for a tool to measure it. They run the code base through a scanner, and it spits out a metric called cyclomatic complexity. Cyclomatic complexity counts the number of branching paths in your code. Every conditional statement, every loop, and every switch case adds to the score. A simple script that runs top to bottom has a score of 1. But the aggregate complexity of a massive legacy payment processor module with hundreds of conditional checks for different currencies, tax jurisdictions, and error states might reach into the thousands. But there is a trap hiding in this dashboard.
Complexity metrics are proxies, not direct dollar cost measures. They are a proxy metric, a signal that a file might be hard to read or risky to change. There is no standardized formula here that converts code health metrics into an audited business cost. You cannot simply multiply a cyclomatic complexity score by an hourly developer rate and get a precise invoice. Why? Because a highly complex, deeply nested file that was written 10 years ago works perfectly and never needs to be changed, costs the business almost nothing. It sits in the repository, executing its logic reliably, requiring zero engineering maintenance. But a moderately complex file that 5 different teams have to modify every single week? That file is bleeding engineering hours. Code complexity is a signal, not a price tag. We actually broke down how architectural friction accumulates in our episode on the hidden cost of microservices, when complexity becomes the product. In that story, the network boundaries themselves started adding friction to every single release, turning simple updates into distributed logic puzzles. If you want the full picture of how architecture becomes a bottleneck, that episode goes deeper into this exact mechanism. But here, the friction is not just about network boundaries. It is about the internal logic of the monolith itself. It is about organizational throughput. To find the actual cost, we have to leave the static analysis panel and look at the assembly line itself. Now move from the static analysis tool to the release manager's terminal, back to the screen we opened in the first 30 seconds, that delivery dashboard. You would expect the biggest cost to be the engineering hours spent writing workarounds. It isn't. The biggest cost is the time spent waiting. This is where the proxy metric translates into actual operating pain. In enterprise software, the real cost is usually the sum of upfront integration work plus long-tail maintenance. These hidden costs usually show up after the initial rollout in on-call load, patching, vendor management, and compliance work. Operationally, teams pay for alert fatigue, incident response, runbook maintenance, capacity planning, vulnerability management, and periodic upgrades when the vendor or framework deprecates versions. The metrics keep pointing to the same pattern. Lead time rises, deployment frequency falls, change failure risk climbs. The right metrics are DORA metrics: lead time for change, deployment frequency, change failure rate, and MTTR, plus engineer hours spent on onboarding, incident response, and dependency upgrades. When technical debt accumulates, lead time stretches from hours to weeks. The measurable signals are rising MTTR, higher change failure rate, more SEV1, SEV2 incidents, slower patch times, increased P95 latency, and larger support ticket backlogs. And in regulated environments, the tax is even higher. In regulated environments, there is also audit overhead, evidence collection for SOC 2, control mapping for ISO 27001, segmentation and logging requirements for PCI DSS,
and security review under NIST SSDF or OWASP ASVS. When the code is messy, proving that it is secure takes twice as long. And we haven't even touched the infrastructure bill. Infrastructure cost is not just licenses or cloud spend. It also includes duplicated environments for blue-green or canary deploys, extra compute for sidecars and proxies, storage and network egress, managed service premiums, and idle headroom needed to meet SLOs. When a team does not trust their code, they spin up a complete parallel copy of the production environment to test the release, effectively doubling their compute bill. They over-provision compute for sidecars because they cannot isolate faults cleanly within the application logic itself. If a memory leak in the legacy payment module might take down the entire node, the operations team simply buys twice as much RAM to buy themselves time during peak hours. That is technical debt showing up directly on the cloud invoice. Hidden costs also include performance tuning, quota management, and data retention storage costs that only appear once the system is live. What we do not know is whether these operational costs exceed the benefits in a given organization, because that depends on workload profile, staffing, and how much automation and platform engineering already exists.
Now pull up the incident timeline in the NOC room and place it right next to that delivery dashboard. The industry assumes the timeline on the left is the ultimate consequence of bad code. But the dashboard on the right is what actually bankrupts the project. Remember that static analysis panel and the code review diff we looked at earlier? We have followed the friction from the developer's local machine through the automated testing pipeline, past the compliance auditors, and all the way to the production infrastructure bill. So we return to our delayed question. Can one code metric really tell you what technical debt costs the business? No, because technical debt is visible in delivery friction before it becomes an incident. Code complexity is a signal, not a price tag. Enterprise productivity is shaped by maintainability, not just local code cleanliness. The outage matters, but the real bill is usually paid long before the pager rings. Technical debt taxes speed before it triggers failure. It is the slow merge. It is the red build. It is the proxy metric warning you that the system is becoming rigid. What we do not know from the question alone is the exact cost for a particular stack, because it depends on team size, traffic, codebase age, and constraints like SOC 2, PCI DSS, HIPAA, or GDPR. But we do know exactly where to look for the symptoms. Return to the object we started with, the engineering delivery dashboard from the opening. The real bill for technical debt is usually paid in slower delivery, higher change risk, and more engineer time spent managing uncertainty, not only when the system fails loudly in public. But understanding the real cost of technical debt opens a harder question. What would it take to replace it without raising the failure budget? This channel follows evidence, metrics, and operational trade-offs to separate code quality signals from the business costs they are often used to explain. Which constraint matters most here? Fault isolation, error budget, or processor choice? See you in the next audit.